Okay, guys, I think we finished up previous pages. Any questions before we get started with new material today? Okay, this page here we actually covered during lab. We pretty much have finished up SN2. What did we cover? We covered things like nucleophiles. That's one component. You've got to have a nucleophile if you're going to do an SN2, if you're going to do a substitution. Then you have to have something with a leaving group, something that gets replaced. That's the substitution. What's going to get replaced? So we looked at that reactant also, or substrate, the thing with the leaving group. Then we also looked at particular reactions like the Williams and ether synthesis, precise examples of substitutions. Of course, we looked at mechanisms, rate determining steps, reaction coordinating diagrams, et cetera, et cetera. SN1, this is it, covered in lab a little bit. SN1 is basically carbocation chemistry. Leaving group leaves to form carbocation. From there, you can do anything we did with carbocations back with alkenes. Because alkene chemistry was carbocation chemistry. Alkene attack made carbocation. Well, here, leaving group leaves makes carbocation. Two different ways to make carbocations. And basically, once the leaving group leaves, then it's carbocation chemistry. Nucleophile can add, just like it added back with alkenes. So there's not much going into it. You know most of it. We went over all this here. There's an important question at the bottom, then we're going to sum it up. Rate equation. What type of, we answered this already, what type of nucleophiles react strictly by SN1? Weak. SN1 is typically when you have weak nucleophiles. Can you identify a weak nucleophile? Hopefully we went over that and we made a statement of how to do that. Everybody good with identifying strong and weak nucleophiles? That must be done if you're going to determine or use nucleophilic strength to determine your mechanism. Weak nucleophile SN1. Okay, any questions? Everybody got your list of questions written down and ready to ask them? Good to go? Summing it up. Summing it up. This leaving group, this handout, summing up this handout. Okay, substrates with leaving group on primary carbon only undergo SN2. Why is that? Why not SN1? Because primary carbocations are very bad. We do not want to form them. Avoid them at all costs, except for mass spec. Mass spec, you will see primary carbocations. Mass spec's a very high energy process. Unless you have to for some reason because you want to avoid them. So you avoid SN1, which involves forming a carbocation. Substrates with leaving group on tertiary carbon only undergo SN1, not SN2. Why? Sterics. And there was like 2 or 3 exclamation points when this was pointed out. Sterics hurt SN2. And you do not do SN2 with the leaving groups on a tertiary carbon. Right? Are we summing it up? Substrates with leaving groups on secondary carbon can undergo either mechanism. If it's on secondary carbon, you're going to have to look at other factors. Okay, let's look. How about the nucleophile? With strong nucleophiles, the reaction will always be bimolecular. That means SN2. Also E2 when we get there. It's also bimolecular. Will a weak nucleophile do SN1? I'm sorry. Will a weak nucleophile do an SN2? Well, that really doesn't address that. It just says, this is talking about strongness. Weak only does SN1. Strictly, or only by SN1 mechanism. With weak nucleophiles, which are lazy, reaction will be unimolecular, SN1, or E1. So you do SN2, the nucleophile has to come in here, and it has to have enough strength, enough get up and go, to come in here and kick that off. But that's only a partial positive. It takes a good nucleophile to attack this partial positive actually and kick that off. It needs to be strong to do SN2. Only strong will do SN2. Thus, weak is left to only do SN1, strictly SN1. Because SN1 involves making cations. Now, it's not going to be primary, so let's add some more carbons here. Okay. Weak nucleophile will get off the sofa and attack this formal carbocation. But a weak nucleophile is not going to be strong enough to come in here and attack the partial positive and kick off the leaving group. It's not strong enough. Well, we don't call it strong, it's weak. But a weak nucleophile will attack that. Weak nucleophiles are lazy. Reaction will be unimolecular, SN1 or E1 when we get there. As long as the substrate is secondary tertiary, right? Because you wouldn't be doing SN1 on primary. So that makes sense. If the substrate is primary, we're under with weak nucleophiles, the reaction will have to be bimolecular. Because with primary, you don't make carbocations, so it has to be a concerted bimolecular backside attack. Finally, of course, a bimolecular reaction with a weak nucleophile will be quite difficult. I could give you a reaction that's just going to be very difficult and it's not going to react. Like reacting this with like water. Is water stronger than weak nucleophile? Weak. How easy is it going to substitute off this bromine? It'd have to be an SN2, right? Because you would never do SN1 on a primary. Well, is this going to do SN2 and come in here and kick that off? The answer is no. This is too weak to do that. It's lazy. Rather sit on the couch and watch reruns of whatever. All right? So reacting this with water is going to be a very difficult reaction and probably not going to react. It's not in this class. Okay? There's some, we have to make statements, and of course there's always exceptions. I think you would prefer that. Or we could just make it all just be open for anything. You prefer statements, right? Strong nucleophiles are what? Anions and sp3 nitrogens? There's many exceptions to that, but how about let's start with that statement. Okay, let's see how we're doing. How we do over here? Get the product, and you need another mechanism to get the product. So asking you to give a mechanism is part of getting the product. Because mechanism dictates product, it also dictates stereochemistry. Anybody got a product for the first one? There's water. Strong or weak? Is nucleophile strong or weak? Weak. Weak. All right. Do you have a leaving? Do you have something with a leaving group so we can replace it, i.e., substitute it, i.e., do a substitution reaction? Right here, right? Leaving group. We can replace it. Replace it with what? Well, hopefully this is a nucleophile. Can that be a nucleophile? Anything with a lone pair can be a nucleophile, but it's weak. Correct. So the mechanism is going to be what? SN1. SN1. So show the product, including stereochemistry. we got here? We got the benzene ring, and we have, what's now going to be on this carbon instead of the bromine? OH. What's the stereochemistry now at the chiral carbon? Racemic. We can indicate that with the star, okay? Racemic. Why is it racemic? Because we know the intermediate here, the key intermediate to carbocation, and water attacks it. Which side does it attack? Both sides. It's planar. It either attacks this way or this way. That's how you get to racemic. Just like with alkenes, we form carbocations and then that got racemic. It's carbocation chemistry. What's the first step in this mechanism? The bromine just has to leave. It has to ionize off. There you go. Plus what if we want to completely balance this? HBr. Bromine minus is going to come back and take that H from the oxygen after it, make it go neutral. Okay? How about the one on the right? Same substrate with the leaving group, but now we have hydroxide mechanism over there. The SN2, because it's strong. And strong bases are bullies. First off, this is hydroxide, right? I was told that I'm supposed to, anytime this, I'm supposed to always show it like this. Because you guys don't know it's ionic. I'm like, come on now. I'm not going to treat my students like first graders. It's ionic. Okay? And we know that that's a spectator ion. It does nothing. It's hydroxide. And it's strong or weak? It's an anion. It's strong. Okay? Mechanism here. SN2. So show the product. Drawing the ring, I'm just going to say phenyl, boom, boom. There we go, and we know SN2 comes with what? Inversion, right? Backside attack. Behind the leaving group. Transition state, planar, inversion. Difference, okay? This is going to give you a racemic product, 50-50 mix of enantiomers. That's going to give you only one enantiomer. It's inverted from this. That reaction is stereoselective, enantioselective. This is optically active. But that's okay, because this is too. Okay, next one over here. Show product there. Going to be that ether. It will be racemic. This reaction is SN1. Methanol, strong or weak? Weak. After oxygen attacks the carbocation that's going to form over here, we lose an H to go neutral. What's the small molecule byproduct here? HI. The I minus will take the H from the oxygen to go neutral, form HI. Everybody understanding how mechanism helps you understand and predict all these products? And, over here. Mechanism over there. Somebody said, I'm not quite sure what it says, somebody said SN1. This is a substrate relieving group, so this has got to be the nucleophile, right? Is that strong or weak?
Strong.
Strong. Do we do SN1 with strong? No. Strong or bully? This is not going to wait for this to ionize. Ionization does take a little time. Here I come. I'm going to come in and do something. Too late. You don't have time to ionize. SN strong nukes. Did we say that on the summing up page? What does it say with strong nuke on the summing it up? Reaction will be what? Bimolecular. That's SN2. So what's going to be the mechanism?
No reaction.
Why do you say no reaction?
Because it's a tertiary carbon.
So you don't want to do SN2 on tertiary?
Carbon.
Exactly. You don't do SN2 on tertiary. So what's the reaction?
There is none.
Actually is one. What is it? Because there's another type of bimolecular reaction. Yes, E2. Summing up page said if it's strong, it's going to be bimolecular, either SN2, but you don't do SN2. This is E2. This is a classical E2. The main point being, you don't do SN2 here. That's E2. And this takes us into the next handout. It will be bimolecular. Okay, down here, some other problems to be working. How are we doing on those? Any questions about those? How are we doing on those? We will have a quiz on Monday on substitution reactions. On Friday, we'll see if there's any other questions about those right there. We already looked at that and this, and okay. That's substitution. Elimination. Well, just like it sounds like, elimination is where we have a starting material, we eliminate something. It's actually the opposite of addition. It's not the opposite of substitution. And it sort of goes a little bit hand in hand with alkene chemistry, because it's the reverse of alkene chemistry. When we reacted alkenes, we were doing addition. This opening page shows a multi-step synthesis, which you'll do more and more of in organic 2. Right here we have a nice E2 reaction. We've got this substrate. Now with eliminations, it is leaving group chemistry. Okay? So you're going to have a substrate with a leaving group, just like substitution. Question?
Can I get one of these handouts?
So here we have, this is an iodine on this substrate. And the iodine has left the building. It's gone. It served as a leaving group. But we didn't just replace it. Nothing's been replaced here. We just eliminated. The I has been removed or eliminated. What else has been removed or eliminated? Also a hydrogen here. Because now there's only one where there was 2 over there. Okay? We have eliminated HI. The formula of the product is missing H and I. That is thus an elimination reaction. We didn't add anything, like we did with alkenes. We didn't substitute because nothing's been replaced. We just simply eliminated. Now, typically when we eliminate, in the most introductory, and everything we'll see, although it doesn't have to be, you're going to get an alkene. So we're going back to alkenes. Now it's the opposite of, remember the alkene chemistry where we maybe added HI? If you add HI, you could have such a product. And we did that. Those were the first types of reactions we did. So we're actually sort of going backwards. This is the addition, alkene addition. Now we're eliminating back to alkenes. This is a common way to make alkenes. But it begins with a leaving group chemistry, or something with a leaving group. There's an example. DBU is a base. It's a little bit unique. We're not really going to see it. It's a nitrogen base. THF is a common solvent. And we're off. Radical bromination we'll cover near the end of the course. Okay. Synthesis of Tamiflu. By the way, it begins with a Diels-Alder reaction. Actually, an Enantioselective Diels-Alder reaction. Okay, here's the general line reaction. This is set up just like the intro to substitution was. We're going to see two different ways to eliminate. Actually, I'll show you three. The third one, I'll say never do it. You guys want to attempt to do it, but never do that. Okay, general line reaction. Some substrate with a leaving group, we're going to have a base. And we're going to end up with an alkene. If you look at this, we have removed an H and a leaving group to put in the double bond, because now there's only one H on this carbon. The leaving group leaves, and when it leaves, it takes on a lone pair, just like with substitution. This may be a minus, or it may not be. Now the base is the one that now has taken the H. And this is an elimination product. Okay, leaving group. We can say something here though. When X is halogen, which is kind of almost most common, although you can have tosylate leaving groups. Leaving group considerations are the same here they were with substitution. But when X is halogen, the reaction is also known as a dehydrohalogenation. Because what are we removing from this molecule? Hydrogen? So we're dehydrohalogenation. Removing hydrogen and halogen. Okay? And terminology is important. Because I don't want you leaving here and someone saying, do a dehydrohalogenation. What is that? They're going to look at you like, did you not take organic chemistry? So while this is most important, terminology is as well, because you've got to be able to speak the language. Okay, an exact example. Maybe this substrate here, leaving group, this guy, which can act as a base. What's a good base? Same as a good nucleophile. Anions, sp3 nitrogens. Is this a good base? It's an anion, yes. This is also called beta elimination. This is the first word in the handout, so probably important. Beta elimination because compared to the leaving group, this is your LG, right? The first carbon is called the alpha carbon. The H that's removed is on the beta carbon. So that's where the term beta elimination comes from. It's really focusing on the hydrogens on the beta carbon. Another important term. We do a beta elimination here, okay? Here's the H that gets removed. We remove these two, and when you do, the double bond ends up between the two carbons. But basically, you get rid of these, and then the two carbons combine, bonding. That's how you get this. Only one H here, And now 2 H's on the end. See, there's 2 H's on the end there. So now this carbon's only making 3 sigma bonds. The H and the Br are now gone, right? The Br becomes Br minus. When it leaves, it takes on another lone pair. Now has 4 lone pairs. And the base now has the H. Right? See, this is the base. It now has the H. So it's specific from the general. Let's look at possible mechanisms for this. How could we do this? All right, I've already kind of given you a little bit. Let's do what we're going to call an E1. Okay. One possible mechanism. Let's see. We got to form a Br minus. What if I just do this? What would that do? I know some of you already don't like this, and that's very good. But let's do it anyway. Boom, boom. It gives that plus what? Yeah? So we've already formed one of the products, Br minus. Anybody not liking this already? Why not?
So, primary carbocation.
Primary carbocation, right. But let's continue on. This is one possible way. Then we'll evaluate and see which one we like best. What can we do next? This would be called what? Ionization, right? Ionization. This would be the rate determining step. Forming carbocations, typically rate determining step. Then how can we get to the rest? What else do we need to do? Now the base, these electrons can come and take the H. But here's where it's a little something different. These electrons, we can actually do it 2 different ways, and the other way makes perfect sense, but it's just usually not done. These electrons then, here, then fall in here to make pi bond. And what does this give? Do we need to do anything else, or are we done? Does that give everything over there? Yeah. This is now bonded to H. That's the thing on the end. What does this arrow mean? If these fall in and make pi bond, what does that give? It gives your alkene. We're done. Okay? This is called an E1 mechanism. E1 is also carbocation chemistry, just like SN1. The first step of E1 and SN1 is the same, making carbocation. The difference is, this thing, instead of adding to the carbocation to give you an overall substitution product, instead it acts as a base and takes a beta hydrogen. The electrons fall in, you get alkene. There are the details here we'll discuss. Okay? If we did a reaction coordinate diagram here, how many intermediates in this mechanism we just did? 1 intermediate. High energy intermediate. What's the rate determining step here? The first step or the second, do you think? Because reaction coordinate diagram, real quick, we start here, we go to carbocation, and then we come back down. Our organic substrate is now neutral again. We come back down. Let's look at this. Is this reaction exothermic or endothermic? Are we going to a higher, more stable or less stable product? We're actually going to reverse. 2 sigma bonds are being broken, and we're forming a pi bond. Is that now lower or higher in energy?
Higher.
It's actually higher in energy. But it's still lower, the product is still much lower than the charged carbocation. Okay, boom. Okay, it's hard to see here, but you got the idea. You may not even hardly need to draw it, right? Which is going to be the rate determining step? Making the high energy intermediate or falling downhill to product? First step. Making the higher, that's the rate determining step. Ionization, the rate determining step. Just like with SN1. Of the two substrates here, how many are involved in the rate determining step? It's just like SN1, only this. We're doing an elimination, but it's unimolecular. Only one is involved in the rate determining step. That's why it's called E1. This over here is fast. What's going on over here? A fast beta elimination. Now we'll use that term in the other mechanism as well, but over there it's going to be concerted. This is fast. Fast meaning easy. Okay, this is one mechanism. But this ain't the mechanism. Why? For this reaction, it ain't the mechanism, because we don't like primary cations. No, bad. But this is E1. Let's try another mechanism. Let's try E2. Now E2, they're both involved in the rate determining step. And I'm not going to take time to draw reaction coordinate diagrams for each of these, because you should be able to do that on your own. They're analogous to previous reactions, same concept. How can we do this a different way? Well, here I kind of have to just show you. It's a little less intuitive, but it's concerted. That means everything happens at the same time, or at least two steps do. And here's another way to do it. What if these electrons just take the H, these electrons fall in, and those get kicked off all at the same time? What does all that arrow movement give? Well, that has the H. What does this arrow mean? These fall in to make pi bond, and then this gets kicked off, and you're forming Br minus. There you go. All together now. That's concerted. That's a concerted beta elimination. How many intermediates here? None. Is there any carbocation here? No. Can you do this? Yeah, I'm telling you, you can do this. This is known mechanism for, called E2. Okay, this is, how many steps in this mechanism, the elimination mechanism? One step. One concerted step. Which step is the rate determining step? That one. Are both of these involved in the rate determining step?
Yes.
Yes. It's an elimination with two things involved. We call it E2. Okay? The concerted beta elimination, the E2 beta elimination. The more difficult, because that is that is a difficult step, but there's nothing to compare it to. That is the rate determining step, I reckon it is. But it's the only step. Okay. There's actually another possible mechanism. And I'm going to show you this one. No book is going to show you this. At least not in this chapter. Books will talk about it maybe in another chapter. But I'm going to show you too, because some of you guys want to try to do it. And it's just not right. So let's look at it. What's another way to get these products? We could do this. And it's going to be different from the previous. What if the base just takes the H and we just do a classical acid-base reaction? Boom, boom. And we make it carbanion here plus that, which is what we need to form there. Did we do this in the previous two? mechanisms? No. Here we make a carbanion. Then how could we get to final products? What if these electrons then move in and kick that off? Right? Would that give everything? This is a third different mechanism. We did not do this in the previous two. This is not a mechanism that we're going to be doing. It's not E1 or E2, which is the only elimination mechanism we're going to be doing. Don't ever want to do this. Because these H's are not acidic. They're not acidic. So we're not going to do classical acid-base reaction to make a carbanion. Also, what do you think would be the rate determining step here? It's two steps, make the anion and then eliminate. Which do you think is rate determining? First or second? Making the high energy anion or going back to the neutral product? Yes, rate determining step. Question here. Does the leaving group leave in the rate determining step in this mechanism? No. What about the previous two? Did the leaving group leave in the rate determining step? It did. In E1 and E2, the leaving group leaves in the rate determining step. In this mechanism I showed you, it does not. The reason I point that out is that's just an assessment that you should be able to do here. Leaving group leaves in the fast step here. See, in organic 2, when you may talk about leaving group leaving in a fast step, you need to understand such. All right. I'm not going to say anything else about this third mechanism. We're not going to make carbanions here. We're either going to do E1 or E2. Such can be done in advanced chemistry, though, but not in this class. Okay. Here's another example reaction. Let's see if we can predict mechanism, etc. If you take this and just heat it in this solvent, or no solvent at all, and if you just heat this thing, it'll eliminate. It'll eliminate HBr. Mechanism for this. Is it E1 or E2? Why E1? This is your base. This is the thing that can take the H. Strong or weak? Weak. Okay? On the sum it up page, weak is always going to be unimolecular. It's lazy. Not strong enough to do bimolecular. This is a classical E1 elimination. Mechanism, first step. Same as a SN1 first step. What's the first step of SN1? Leaving group leaves. Same as E1. Leaving group leaves. To give carbocation. Okay? This can be facilitated by heat to get the ionization to take place. All right? What next? Something now has to take the beta hydrogen. What can take the beta hydrogen? What base are you looking at?
Well, I guess the lone oxygen is also
Right, this could. This could act as a base. It's a weak base. Anything with a lone pair that would act as a base. Actually, also, yeah. You see, the Br minus could actually come in here and take an H, and these move in. And you see how we can get this and that. And you see how that didn't do anything at all. That's what I said. You could do this with no solvent at all. Question?
Wouldn't it make a cis product?
I can't hear you.
If the bromine takes up hydrogen and the electrons go down, would that make a cis product?
Excellent question. We're heading there. Excellent question. Looking at stereochemistry, because this product is stereogenic. Alkene is stereogenic. It can be cis or trans. I drew trans. Very good. Well, why do you say we should give cis? Because these two groups are cis here? Very good. But this has free rotation. That's a sigma bond, free rotation. Okay? Right, remember the models? Free rotation. How's it going to prefer? Like this or like that? Syn or anti? Yeah. This thing is in equilibrium, but this is going to be favored. It can rotate. And this can here. But this equilibrium is like this, right? Very excellent point. I just didn't talk about that. We will coming forward. But yes, free rotation. Previous principles are always going to be there. Right? You see how this could just be solvent, or if you just heat this by itself, like neat, it could, if it gets up to like 200, 300 degrees, it start just giving off HBr through this mechanism. What mechanism is this? What did we just do? What? If we eliminated, is it an E1 or E2? There you go, classical E1 mechanism. Okay. But we kind of know it's going to be E1. Because to do an E2, you have to have a what? Strong base. Summary page before. It summed up E1, E2 as well. Any bimolecular reaction needs a strong nucleophile or a strong base, because bimolecular is a concerted thing. It requires strong. There's no strong base here. E1. Can you do an E1 here? What type of cation did we make? Secondary? Secondary is okay. Not as good as tertiary, but it's okay. Thermodynamics and entropy. We already talked about thermodynamics. This reaction is going to be endothermic, right? All right, we'll just do it here. Endothermic. But you can get your calculator out and look at bonds broken, bonds formed. It's going to be endothermic because we're making a weaker pi bond. What about entropy? Is this reaction favored by entropy? It's not favored by thermodynamics. But is it favored by entropy? Why? Yeah, if you just exclude this, or even if you include it, you get the same answer. It's easier. One molecule becoming two. It's becoming more random. Entropy is favored. Entropy is what drives this reaction. Since entropy is favored, does heat help the reaction or hurt it? Gives free energy. Entropy is multiplied by what? Temperature, right? T delta S? If delta S is favorable, do you want temperature to be high? Will high temperature help it? Help the overall? Yeah. High temperature drives this reaction because entropy is favorable. Okay, let's get into his particulars. Regiochemistry. If you do beta elimination here, chlorine's a decent leader group. It's not as good as bromine and iodine, but it's okay. If you beta eliminate, you beta eliminate here, you're only going to get one product. Only one possible product because you only have beta hydrogens here. You remove HCl, you're going to put double bond in here between where the two were. There you go. And this product has no stereochemistry. It's not stereogenic. So we don't have to worry about cis or trans. So that's it. By the way, this would have to be a what? E1 or E2? Have to be E2 because leaving groups on primary carbon. You would never do an E1 here, right? E1 involves carbocation. But look down here. If you do a beta elimination here, there's actually 3 theoretical products. Why? First off, we can beta eliminate on this side. We can call that maybe HA. Now there's 3 H's here, but I'm only drawing in 1. If we eliminate it over here, we'd put double bond between carbon 1 and 2. But we can also eliminate over here, and I'll call that HB. There are 2 H's here, I'm only showing 1. If we eliminate it over here, we put double bond between carbons 2 and 3. But hold on, this product is stereogenic, so it could either be E or Z. Question here is, which of these 3 are you going to get? And that's what we need to be able to answer. Which alkene will be formed? Depends on a variety of factors. Here we go, let's answer that question. First off, the most substituted alkene is the thermodynamic product. We already knew that though. Right? These are stereoisomers, so let's consider these 2 regioisomers. Which one's more stable? This one is di-substituted. More stable. It's called the thermodynamic product. That's what we're saying here. In the context of elimination reactions, it's called the Zaitsev product. Okay? That's the Zaitsev product. The more substituted terminology. All right. We're pretty much out of time. Please be ready for this coming. Okay, we get into the particulars. Hoffman product. Lab upstairs. Have a good day, guys.